Welcome to Lecture 4B, entitled Differentiability. The material for this lecture comes from section 15.3 of the textbook, including some additional material which is not found in the textbook. The objectives of this module are to extend the concept of differentiability for one variable to the multivariable case. The concepts and definitions covered in this module are differentiability and its relationship to continuity. As usual, the second slide is just an outline of the talk itself in terms of the 10 different topics that will be covered, so we'll just move on. All right, so let's look at the definition of differentiability of a function with one variable. And so we start with the definition of derivative, which is stated here. F prime x equals the limit of this difference divided by h, and this is provided that the limit exists. Over on the right is just a figure basically showing a particular example that we're taking here, which is that y equals x squared. It's a parabola. And then x equals a being the point of interest, which is basically appearing at this point here on the parabola, which would be a y coordinate of a squared. So if we basically apply the definition of the derivative using this function, make the substitution for a plus h and a, simplify and let h go to 0, then in the limit f prime evaluated a is 2a. This just represents the slope of a tangent line at the given point shown here. So the definition of differentiability for one variable basically is stated here. And it's as follows, that the derivative of the function y equals to f of x is differentiable at x equals a, provided the limit f prime x, which is this limiting process, exists, and the change delta y, which is just f evaluated a plus delta x minus f of a, is equal to delta y f prime x delta x plus epsilon 1 delta x, where for a fixed value of a, epsilon is a function that depends only on delta x, so it's just a function of delta x, and with epsilon 1 approaching 0 as delta x approaches 0. So function is differentiable on an open interval I if it's differentiable at every point of I. So you would have to repeat this process for all points over an interval to determine whether or not it's differentiable over at every point of I. So the alternative definition, aside from this one, is invoking a geometric principle, that is, that a line is tangent to a curve, and it's intuitively easier to grasp, as will be shown on the page after the next example. All right, so let's do an example, the differentiability of a function with one variable, and we're given a function y equals x squared, and the operating point would be x evaluated at a, which means y would be equal to a squared. And so using the definition of differentiability from the previous page, we need to determine delta y on the left-hand side. And so all I've done is basically written it out. So delta y is a plus delta x minus fa. Make the substitution given that we're dealing with a function y equals x squared. And then after simplification, we find for delta y on the left-hand side, we have this expression. Then we find delta y on the right-hand side. On the right-hand side, we have delta y as f prime x delta x plus epsilon delta x. Of course, the objective is to figure out what epsilon is. Anyways, if we make in the substitutions for f prime x, then we end up with 2a delta x plus delta x squared. And this basically is equal to 2x delta x plus epsilon delta x. All right, so now we let x go to a, in which case basically the term involving x here becomes a, and so we end up with 2a delta x plus epsilon delta x, which is the term that you see here. So the objective is to find out what is epsilon 1. So by making the expression, equating the two together, that is, we equate this expression with this expression. After simplification, we find that epsilon 1 equals delta x. All right, so that's basically the outcome. This is where we want it to go, and so now we go back and check. What are the conditions for differentiability? First of all, is epsilon 1 a function of delta x? The answer is yes, it's right here. Does epsilon function of delta x approach 0 as delta x approaches 0? Yes, it does. As delta x goes to 0, epsilon goes to 0. And does f prime a exist? And the answer is yes, because we were dealing with a function which is analytic. So a conclusion is that all three conditions of differentiability definition have been satisfied, and therefore the function y equals x squared is differentiable at x equals a. Okay, so this is just a graphic that you can play with. This is one clearly indicating a discontinuous derivative. And so what will happen is as you move down this curve, your tangent line basically moves with it. And then at this point here, it suddenly flips from being in this direction to being in this direction. So at this point here, clearly the condition of differentiability basically does not exist. And you can just see that where the program doesn't quite know what to do at this point. Anyways, you can look at this just for argument's sake if you wish. All right, so now we're looking at the alternative approach for definition for differentiability, invoking a geometric principle. And so let's basically see how we state this one. First of all, we'll let y equals f of x, where x is an element over a certain interval, be a function of one variable. Suppose that the derivative f prime exists at the point x equals a. And now what we do is define the linear function, which turns out to be the tangent line at a given point a. Define that as being f of a plus f prime of a times x minus a. This is in fact the definition of a line with an intercept and a slope. And this basically passes tangent to a point of interest, which is a point x equals a. All right, we say that f is differentiable at a if the limit as x approaches a of e subscript d over dxa equals 0, and definition of these two entities are shown here. E of d is just the difference between the function and the tangent line. In other words, an approximation at a given point on the line, on the curve. So the difference between these two is e of d, and dxa is just the difference between x and a. And so for this to be equal to 0 would mean that e of d approaches 0 faster than dxa, that is x minus a, approaches 0. All right, so meaning-wise, what is e of d? It represents the difference between the value of the function on the curve and on the tangent line. So that's basically this distance that you see here. And the d of xa represents the distance between an arbitrary point x and the point of interest x equals a. So that would be this distance that you see here. If either the derivative f prime a does not exist or the limit is not 0, then f of x is not differentiable at a. Now, you can obtain the expression limit xa ed d of x equals 0 by replacing x with a and h with x minus a in the previous expression. In other words, starting with this limit expression, we can basically evolve to the expression that we see here. All right, so now let's extend the notion of differentiability to two variables. All right, and I've just basically repeated here what the definition for differentiability for one variable was. And just to repeat, we have basically that the derivative f prime x was just a limiting process of the difference between 2 points divided by the distance h. And we also said delta y had this form and equals also an alternate form. But we basically said epsilon 1 would be some function of delta x. And then in the limit, as delta x goes to 0, epsilon goes to 0 as well. All right, if these conditions are all satisfied, then the function is differential on open interval I and at every point I. Now, using the same platform, we can extend essentially the definition of differentiability to the two variable case, except we now have two derivatives to consider, both of being partial derivatives. So let's see what the difference is. First of all, it's a function of two variables. So we have a function z of x of y. The function is differentiable at ab, provided that f partial x evaluated at ab and f partial y evaluated at ab exist, and that the change, this change now takes on a slightly different form. Delta z is now x evaluated at a plus delta x, and y component is evaluated at b plus delta y, minus the original value, which is at a and b. And this should be equivalent to delta z, where this now basically is linearly related to delta x and delta y. And also we have again these terms, an epsilon 1 delta x and an epsilon 2 delta y. This is f partial x, this is f partial y, and epsilon 1 and epsilon 2 can only be functions of either delta x, delta y, or both. Okay, and as the delta x, delta y go to 0, then epsilon 1 and epsilon 2 go to 0. Right? If these conditions are satisfied, then basically it's differentiable at every point of R. All right, so we would like now to take this and see what this looks like in example form. All right, so let's consider now as sort of an example that is proving differentiability of a function with two variables. We'll keep it rather simple, otherwise basically it gets too complicated in terms of the manipulation of algebraic quantities. So we'll start with this function here, z equals x cubed plus xy squared plus 7, and we're going to prove that it's differentiable. So first step would be to find f partial x at some value a of b, and so we're applying the actual definition of a partial derivative here, but using this as our function. And so we're basically substituting for x a plus h here, and for x a here, and in both cases y is b. And if we go through these calculations, you'll see that ultimately as h goes to 0, there's some cancellation, and we're just basically left with terms of 3a squared from here and b squared. Similarly for f partial y, in this case y is perturbed, so y becomes b plus h. In this term it's b. X remains at some constant value a. Divide by h, and the limit basically we can see in this last term here. You can basically cancel through by h, one of the h's on the numerator. And then if you take the limit here, this term goes to 0 and we're left with 2ab. So the third step here after computing the two partials was to compute delta z, which is defined as the difference between the two functions. That is one where you're perturbing x and y, minus the original value, which is a function evaluated ab. And so this is purely numerics. You just have to make the substitutions of a plus delta x and b plus delta y into this expression here, subtract away the same function with a and b substituted for x and y. And then in the end, we end up with this term, this expression with 8 individual terms involving delta x's, delta y's, and combinations thereof. All right, so now let's basically move to the next step. I basically have delta z as is equivalent to the f partial x, delta x plus f partial y, delta y, plus some epsilon 1, which is a function of delta x and y, times delta x plus epsilon 2, some function delta x and y times delta y. And so we just make the substitutions based on the expressions from the previous page. And so for delta z from the previous page, basically, we have the expression which would be the term that you see here. They're the 8 terms. That's just the left-hand side corresponding to this. And the right-hand side, which corresponds to this, would be what we see here. Right? And so we have these two which are being pre-computed, these two pre-computed delta x, delta y, and that corresponds to the 3 terms that you see in blue. So now what we do is we equate the left with the right. And so, for instance, this term basically, and this term, and this term, and this term essentially have sort of commonality. And this term have commonality, and the green terms have commonality. And so from this we can extract the fact that 3a delta x squared plus delta x cubed can be written also as some epsilon 1 times delta x, from which we can compute delta epsilon 1. And notice it's a function of delta x. We can do similarly for E2, where we equate basically E2 delta y with the terms only involving delta y, and simplifying by dividing through by delta y, we find that this epsilon 2 is a function of both delta x and delta y. All right, so all the computations are completed. Now we just go through and check to see all the conditions are satisfied. So first is to check if epsilon 1 is a function of delta x and delta y. The answer is yes from here. Check to see epsilon 2 is a function of delta x and y. The answer is yes from here. Next would be to determine if the limit of epsilon 1 and epsilon 2 as delta x and delta y approach 0 is equal to 0, and you can see clearly from that that will be the case. Answer is yes. And finally, do fx and fy exist? And yes, they do exist. So in conclusion, all conditions of the differentiability definition have been satisfied. Therefore, the function z equals x cubed plus xy squared plus z. 7 is differentiable at x of y equals a of b. All right, so in 2D, we can look at, again, the notion of derivatives. So here's an example. We have a smooth surface. And if you were basically to compute partial derivatives here, you basically would essentially be able to match at every point on this surface. Whereas here we would run into difficulty right at this point here. If you draw a line, if you draw a tangent in any particular direction here, you'll find that here the slope is in this direction and here it's in this direction. But at this point you would be having a problem to figure out how to even define things. So in fact, this is an example here at this point where essentially differentiability condition is not satisfied. So remember, in the case of one variable, we said there was an alternate definition was motivated by a geometric principle. In this case, with two variables, we have the same idea, but in this case, rather than dealing with a tangent line, we're talking about a tangent to a surface. That is a plane that's tangent to a surface. So we can take any flat plane and touch it on this surface, and it will touch at only one point. Okay, this is intuitively easier to grasp this way, and so we're going to detail this on the next page. All right, so this is the differentiability of a function with two variables. So let's look at how this definition is set up. First of all, we let z be f of x, y, and this is part of the domain D. This would be a function of two variables. And we're saying that the partial derivatives fx and fy exist at the point x of y, a, b. And now we're going to find a linear function, which is a tangent plane that touches the surface at the point a of b. And this is the z component evaluated at x, a, y equals b. So this now becomes basically the functional that we're dealing with, which is the equation of a tangent plane. Now, why would you say that? Because it's linear in x and it's linear in y. And so this would be equivalent to the z value. So this expression looks very similar to what we saw very early in the course when we had discussed basically the equation of a plane. And f partial x is here, that has to be computed, f partial y has to be computed. So then we say that f is differentiable a of b if the following limit is 0. And so the e of d basically would be the difference between the function and the approximation that of a tangential plane, whereas this expression d is the magnitude, that is the norm or the distance, value of x minus a and y minus b. All right, so if you have a circle, right, then it's basically the distance from the point, any point on this circle, to the point of interest, which would be the point x equals a, y equals b. And so this is the difference in the definition when we move to two variables, is that this distance now is not just along the x-axis, but it can be on an xy plane between any point here in this region and the point of interest. All right, so picture-wise, what would this mean? Well, here's the tangent plane shown in blue. Here's the surface. This distance between any point on this plane and this curved surface is this distance ED that we're looking at in the numerator. And the distance is this that we see here, which is just the region of interest on the xy plane between the point and the point of interest. Anyways, you can play with this simulation if you wish. This is just basically showing how we can extend the notion of differentiability from one variable to two variable using a geometric principle. All right, so now let's consider differentiability of a function with two variables by way of an example. And so the specific example is given here. We're to determine if the following function is differential at the point 1, 1, and f of x, y takes on the value of x minus 1, y minus 1 divided by the square root of x minus 1 squared plus y minus 1 squared if x, y is not equal to 1, 1, and it takes on the value 0 if x of y is equal to 1, 1. So the first step is basically to prove that the partial derivatives f of x and f of y exist at location 1, 1. And so we basically use the formal definition of the partial derivatives. And so fx11 means basically you keep the value of y constant at 1, and you perturb the value of x, so that becomes the limit of h approaching 0. F is evaluated at 1 plus h1 minus f evaluated at 1 divided by h. And the limit of that turns out to be 0. Similarly, taking the partial of f with respect to y evaluated at position 1, 1, we can see in this case that we hold the value of x constant at equal 1, and we perturb the value y, and similarly in this case we end up with a value 0. That is, the numerator in both cases equal to 0. All right, so the next step is to compute the distance between the actual surface and an approximation of the surface, which we consider as a tangential plane, and that plane touches this surface at the point, some point evaluated at x equals 1, y equals 1. And the approximation, that is the tangential plane, is given here. And so this is basically the evaluation at the point of interest plus the partial derivative with respect to x times the distance between some value x and the actual value 1, which is the point of interest, plus f partial y evaluated at 1, 1, and a difference between the value, some value y, and the position of interest, which is 1. So we can basically compute this here, and so in the second step, the second line that you see here, if we take the difference between those two, make the substitutions, then we find that we end up with a value of E subscript D, which takes on this form here. Next step is compute this distance. All right, so this distance would be just the norm, and this would be just the square root of x minus 1 squared plus y minus 1 squared. And now we take and divide these two, and by dividing these two, those two square roots that will appear in the denominator end up just giving you x minus 1 squared plus y minus 1 squared. And so we have to evaluate this limit, and if the limit goes to 0 for all possible cases, then we know basically its function is differentiable. However, this is not a simple case to consider, so we make a substitution as we've done before. We're going on the assumption the limit does not exist in this case. We'll see that, in fact, it's a correct assumption to make. So what we're going to do is we're going to let y equals v sine u plus 1. I'm going to let x equal v equals u plus 1. V is greater than or equal to 0, and u is between 0 and 2 pi. Now, why would we do that? Why? Because we see this x squared, y squared scenario all over again. And also, this is a one-to-one mapping, so we're not basically double counting. So if we make these substitutions in to this expression, right, and given that basically we need to figure out, what would the limit be if you're going 1, 1? How does that transform into conditions for v and u? Well, in this case, v would have to go to 0. So v going to 0, u can be anything within this range. And you end up now with a transformation that makes this expression now v squared sine u cos u divided by v squared. Well, that means v squared is basically cancel, and we're just left with the limit of sine u cos u, v going to 0. Of course, there's no v here, so it doesn't affect the expression. However, it's clear that depending on what the value of u is, you get a different limit. And as a result of that, basically, there's no way that this can be 0 for all possible values of u. Right? And therefore, we basically can say that the function is not differential at the point 1, 1. All right, so to look at some special cases, normally it's difficult to do all these types of calculations because at some point you may not be able to prove if the limit exists or does not exist, or if the limit goes to 0. So these are specific cases which are actually convenient because it gives you an answer immediately. So one of them is the conditions for differentiability. Theorem 15.5, and it states that suppose the function has partial derivatives fx and fy defined in an open set containing ab, with f partial x and f partial y continuous to ab, then we can say f is differentiable at ab. The biggest problem here is that we have to prove continuity of the first order partial derivatives of f, x, y. On the other hand, you can take a contrapositive argument and sense if the function is not differentiable, then at least one of the partial derivatives, fx or fy, is not continuous at ab, or there is no open set containing ab such that the partial derivative fx or fy is defined at all points on that set. So sometimes actually the contrapositive argument is the easier approach to take. So there are these two options. This is a more difficult one potentially, whereas this may be the easier one of the two. All right, so now let's consider the differentiability of a function with two variables. And this is a special cases example. We want to prove that according to theorem 15.5, the function of f(x,y) equals x times sine y over y is differentiable at 0, 0, where in this problem we're imposing the condition that f of xy equals x at y equals 0. We can do this because if we look at the function itself, it's broken up into one function of x and one function of y. And by the product rule, if we can prove that the limit of x exists and the limit of sine y over y exists, then basically the limit of f of xy will exist at the point 0, 0. For the second part, sine y over y, because it's only a function of y, we can use L'Hopital's rule to basically show that the limit of sine y over y as y approaches 0 is equal to 1, and that, hence I'm just imposing the condition that that equals 1, and hence fxy equals x when y equals 0. And I've just put the domain there as just excluding y not equals 0. All right, so let's review typically the options for case where you have y equals 0. In this example, we basically have imposed the condition and make it clear that a value exists at y equals 0. But you can have a function where, for instance, at a boundary point, you basically don't impose the condition, in which case you leave it open. In this case, there's a condition imposed, which means we've chosen option 1. All right, so we now want to go through the process to proving that differentiability. So the first step is to determine if f partial x and f partial y are defined on an open set. That includes the case of y equals 0. So for f partial x, it'll be sine y over y for y not equal to 0, because the function's perfectly well behaved. And it'll be fx equals 1 for y equals 0 if we apply the formal definition for f of x, which means you have to essentially have a difference divided by some variable, which in the limit goes to 0. Similarly for f of y, as long as we're not dealing with y equals 0, then essentially the function is well defined. Whereas for the case where y equals 0, we can again use the formal definition of y, and we can show basically that f of x equals 0 for y equals 0. And I've shown here below, for example, this is the definition that we would use for computing f of y. Be sine of h over h minus 1 divided by h. H being the function evaluated at 0, 0, which basically imposed the condition 1. And so if you expand this out, then what we can do is expand sine h in terms of a Taylor series, and then the only term of interest, which would be the lowest order, which is h, but as h goes to 0, this term goes to 0, and hence the limit of f partial y, h going to 0 is equal to 0. Here again is the Taylor series expansion for sine of h. F and fx and fy partial are analytical functions for y not equal 0, and are defined at y equals 0, and thus are defined on an open set. So essentially step 1 is completed, and we move on to step 2. And we have to determine if f partial x and f partial y are continuous at 0, 0. So again, for continuity, we have 3 rules that basically have to be satisfied. That is all of them. So the first rule is f partial x and fy exist at 0, 0, and yes, they do. We've just basically shown that to be the case. F partial x 0, 0 equals 1, and f partial y 0, 0 equals 0. Okay, rule 2 is that the limit of f partial x and f of y exist at 0, 0. And so using L'Hopital's rule for f partial x, as y approaches 0, we end up with 1. And for f partial y, we'd be using the product limit law. So if we have the limit of x equals 0 is equal to 0 as xy approaches 0, 0, and the limit of the expression that you see here as xy approaches 0, 0 equals 0 by L'Hopital's rule, and therefore basically by the product limit law, the product of the two, the limit of the product of the two is exists, and in fact it will be 0, and it's just the product of the two. All right, so check 1, check 2, and now rule 3. Rule 3 is that the numbers, the partials, should be equal to the limit. We have fx 0, 0 equal 1, and the limit of xy approaching 0 of sine y over y equals 1. So these two are the same. And f partial y is 0, 0 equals 0. And the limit as xy approaches 0, 0 of this expression is also 0. So these two are identical. Hence, rules 1 to 3 are satisfied for both partial derivatives, and therefore f partial x and f partial y are continuous at 0, 0. All right, notice that step 1 and step 2 are satisfied, and so now we can state that the function's differential at point 0, 0. Now, if you wish, these are graphs of the specific function where I basically shown the original one, f partial x and f partial y. And if you want, you can basically click on this URL to look at this and move the object around if you're interested in doing so. All right, so now what about the relationship between differentiability and continuity? All right, for one variable function, differentiability implies continuity, and so let's just put the theorems down for that. So in the 1D case, one variable case, if a function f is differentiable at x equals a, then it is continuous at x equals a. The contrapositive argument, which is basically taking everything in reverse and negating, if the function f of x is not continuous at xa, then it is not differentiable at x equals a. We can extend this concept, extend this to the multivariable case, and then state it in terms of the following theorem. The proof you can find in the textbook if you want to look at it. So for the case of the two variables, if a function f is differentiable at a of b, then it is continuous at a of b. The contrapositive argument would essentially say that if the function f of xy is not continuous at a of b, then it is not differential at a of b. All right, let's consider another example. Example 4, we're going to apply the definition for differentiability directly. So in this event, basically we're given that the function is x times y to the power of 1/3, and we want to prove that it's not differentiable at the point 0, 0. And so first step is just to determine the existence of the partial derivatives, and we use the formal definition to do the computation of the partial derivatives. And so, for instance, the x value is perturbed from its original value of 0. Y is kept at 0, but you'll find that the numerator in this case becomes 0. And so irrespective of x approaches 0, the limit of this is 0. Similarly, fy, we have a similar result. And we find that the limit as y approaches 0 is still 0 because the numerator is 0. So the outcome is that both partial derivatives exist. All right, so next thing is the existence of a limit and that the limit equals 0. And so we have to basically determine the difference between the function and approximation of the function, which is a tangential plane. And we make the substitutions for f of x, f of y. This is x minus the value of x at the point of interest, y minus the value of y at the point of interest. And if we make the substitutions of the values in here, we find that we're only left with f of xy, which is x of y to the power of 1/3. The distance is the distance between x and 0, y and 0, which is the norm, which will be, by definition, x squared plus y squared. And now we want to prove that the limit for this does not equal to 0, and a simple way to do that will be to choose the path y equals x, make the substitution in here, and we get x to the power of 2/3 divided by square root 2x, and so we end up with 1 over square root 2. X is to the power 1/3 is in the denominator, but as x approaches 0, this becomes infinity, which is not equivalent to 0. The limit does not exist, and also it does not equal to 0. So conclusion is that the function is not differentiable at 0, 0. Well, this concludes lecture 4b. Thank you for listening.